Blood hydrostatic pressure. What is it? Blood hydrostatic pressure is the mechanical force that blood within our circulatory system exerts on the walls of the blood vessels that contain it. Blood hydrostatic pressure, or BHP, originates with the contraction of the left ventricle. We know that BHP favors the outward movement of fluid from the capillaries, and it's much higher at the arterial end than it is at the venual end. So this means pressure drops as it moves through the capillaries. We're going to work some problems that illustrate this. It's not only important to realize that BHP drops as blood flows through the capillaries, but understanding the reason why. The main reason is because capillaries are very small and offer a lot of resistance. The fluid inside the capillaries, because it's in a closed container, is under a fairly high hydrostatic pressure. There's also fluid outside the capillaries in the space called the interstitial space that's under very little hydrostatic pressure because it's not within a container. The pressure exerted by this interstitial fluid is known as IFHP, which stands for interstitial fluid hydrostatic pressure, and it's equivalent to 0. There is another pressure that we need to consider when looking at the interstitial fluid. It's called the osmotic pressure, or interstitial fluid osmotic pressure. And a typical value for IFOP is 3 millimeters of mercury. The reason the interstitial fluid has an osmotic pressure is because it contains many solutes. Because blood has more solutes than interstitial fluid, it has a greater osmotic pressure. A typical BOP is 25 millimeters of mercury as compared to a typical value of 3 for IFOP. So there are two different forces at work, hydrostatic forces and osmotic forces. Hydrostatic forces are pushing forces that favor filtration, which is the outward movement. Osmotic forces are pulling forces that favor reabsorption or inward movement. If we know the hydrostatic pressures and osmotic pressures, it's possible to calculate the magnitude and direction of fluid movement at both the arterial end and the venual end of a capillary. See if you can place arrows in this capillary with these values. I'll show you how to work the problem in the next slide. Here are the directions in which you should have drawn your arrows. Let's look at each of the values. At the arterial end, there's a hydrostatic pressure, or HPA, of 32 millimeters of mercury. Because it's hydrostatic and it's generated within the blood vessel, it's an outward pushing or an outward movement. The HPV is the hydrostatic pressure at the venual end. And again, it's a hydrostatic pressure, so it pushes outward and is generated from within the blood vessel. The BOP, or blood osmotic pressure, is 25 millimeters of mercury. And because there are many particles in the blood, these particles tend to draw water toward them, so it's a pulling movement. The IFOP, or interstitial fluid osmotic potential, is due to the presence of solutes in the interstitial fluid. And again, it's a pulling pressure. The IFHP is interstitial fluid hydrostatic pressure, and there is none, so the value is 0. Based on the previous slide, let's calculate the direction and magnitude of movement of fluid at both the arterial and venual end. Let's look first at the arterial end. The outward movement of fluid there is 32 millimeters of mercury and 3 millimeters of mercury. The inward movement is 25 millimeters of mercury. If you add 32 and 3, you have 35 millimeters of mercury moving outward and 25 millimeters of mercury moving inward. The net gain, or the net difference, is 10 millimeters of mercury favoring filtration, which is the outward movement. At the venual end, the outward movement is 15 millimeters of mercury and 3 millimeters of mercury. The inward movement is 25 millimeters of mercury. If you add 15 and 3, that's 18, and subtract 18 from 25, and the difference is 7 millimeters of mercury, and this favors reabsorption, or the inward movement of fluid. Based on the previous slide, you should now be able to answer these questions. The magnitude of movement at the arterial end is 10 millimeters of mercury, and since it favors filtration, this is the outward movement of fluid. The magnitude of movement at the venual end is 7 millimeters of mercury and favors reabsorption, so it's the inward movement of fluid. Here's a second problem for you to work. See if you can place the arrows before you look at the answers on the following slide. This is how your arrows should look. Remember that hydrostatic pressures are pushing pressures and osmotic pressures are pulling pressures. Let's calculate the direction of movement and the magnitude at both the arterial and venual end. At the arterial end, the outward forces are 40 millimeters of mercury and 2 millimeters of mercury, and the inward force is 28 millimeters of mercury. If I add 40 and 2, I have 42, and from that I subtract 28. The net value is 14 millimeters of mercury, and this favors filtration. At the venual end, the outward movement is 14 millimeters of mercury and 2 millimeters of mercury, and the inward movement is 28 millimeters of mercury. I subtract, and the net value is 12 millimeters of mercury, and this favors reabsorption. If you look at the problems that we've worked, it should be obvious that there's not a balance between filtration and reabsorption. There's more that goes out than comes back in. What happens to this fluid? It's picked up by the lymphatic system. If you continue to leave fluid outside the vessels, it would create a number of different problems. So we have to somehow get the fluid back into the vessels, and it's the job of the lymphatic system to do that. I found this problem on the internet and thought you might like a little bit more practice. It'll be a welcome change to see a problem written by somebody who can actually draw. So take a look at this, see if you can calculate the magnitude and direction of movement at both the arterial and venual end, and then scroll on to the next slide for the answers. I hope these were your answers. If not, and you need help with these problems, please let me know. I would be happy to help you anytime.